Greetings! Welcome to Lab 4, Part 2 on confidence intervals. So we're going to spend a little more time talking about how a confidence interval is built and some of the controls or some of the things that you have to adjust the width of the interval and thereby perhaps some of the accuracy or precision of your interval. So let's go back over to the whiteboard here, back to R real quick and go read the problem statement. It says in exercise 4.9, which is what we're going to use kind of to tackle this concept, we're looking at the width of a confidence interval. And it says, earlier in chapter 4, we calculated a 99% confidence interval for the average age of runners in the 2012 Cherry Blossom Run as 32.7 years to 37.4 years based on a sample of 100 runners. How could we decrease the width of this interval without losing confidence? So let's go back to the whiteboard here and see if we can maybe make sense of this with the drawing. So what we're going to do is we're just going to draw a number line and use the number line to kind of help us out here interpreting what the heck is meant by the interval. All right. So if we notice that original level that was set here was the confidence level was 99%, right? So since they set a 99% confidence interval, what that means is that the z stars that were calculated set the width of the interval so that if we take our x bar right here, we took x bar and we added to that the z star. Notice that z star came from the 99%. Remember, that one I will draw you a normal distribution over the top of. That if this is the normal with mean 0 and standard deviation 1, in other words, the standard normal, then we know that 99% of the data fell between this negative z star and this positive z star. In other words, those are the numbers such that 99% of the data fell within that interval between there and there, okay? So there's that z star. That's where they're saying that's got to be fixed. We can't change that number. They want to keep the confidence equal to 99%. In other words, they want C to stay at 99%. Well, what else is a part of the endpoint here? Well, it's also the standard error, right? So we know that that's x bar plus z star times the standard error, and down here it's x bar minus z star times the standard error. So let's go remind ourselves really quick what the standard error looks like. How do you calculate the standard error? Well, the standard error is given to be sigma divided by the square root of n. Well, we typically don't know sigma, so what we say is, well, we're just going to approximate that standard error with s divided by the square root of n. And so the confidence interval, the endpoints of your confidence interval can be thought of for finding the confidence interval for the mean as x bar minus z star times s over the square root of n to x bar plus z star times s over the square root of n. Okay, now of these numbers that we use to create this interval, the ones that we have control over, the only ones that we can actually make any difference with, are the z star. That's based solely upon the confidence. You set the confidence, and that's going to give you your value as z star. The other number that we have control over is n, and that's our sample size. So notice that if we increase our sample size, what's going to happen to the standard error? In other words, the stuff that I've got in the colors right here, n and z star, those are the two things that we have control over and thereby give us the levers and the pulleys, so to speak, to adjust this distance, this width here, between x bar and the endpoints of the interval. Well, notice that if I increase n, is that if as n gets bigger, what happens to the standard error? The standard error gets smaller. There's an inverse relationship between them. In other words, the larger the sample size is going to be, the less standard error there's going to be. And intuitively, that makes a lot of sense because the more data you have, the less variability there should be in your estimate of a parameter. You should have a better sense of what the parameter is the more data you have. In this case, the parameter we're trying to estimate is the mean. We're trying to estimate mu using x bar. So that's another way that we can shrink the width of our confidence interval without changing the confidence level, is we can increase our sample size. So if you increase the sample, what that infers to us, or sample size, excuse me. So we increase the sample size and infers to us that the interval width will get narrower. So the interval is smaller, I think is how the textbook says it, or narrower, however you'd like to look at it. Okay, so let's go ahead and type that up in our R Markdown file that we've got going here. So let's go back over to RStudio, and let's come in and type that in here. So if we increase the sample size, the SE, that's the standard error, will be smaller, and therefore, or thereby, make the interval smaller, or make the, let's just say the width, make the width of the interval smaller. Okay, well, hopefully that's clear. If you have any questions on any of those, please do not be shy about posting questions in the discussion board, and I'll see you back here for the next one.